Hello everyone. So we are studying module number 4. This impact of jet is over. Were studying turbines, impulse turbines especially. In that introduction to turbines, general layout, heads and efficiencies, classification of the turbines, Pelton wheel, its component parts, working principle, velocity triangles, maximum power, efficiency, all this we have done. We are just left with working proportions. That is what we are going to do now. So in working proportions, what it mainly deals is the design of a wheel. Now the design means to determine sizes and numbers of various components of Pelton wheel. Now here the procedure is given to design the Pelton wheel provided to produce power P. This has to be predefined with wheel running at n rpm revolutions per minute and with overall efficiency eta. If these things are defined, we can design or give the proportions of the sizes of Pelton wheel. If some of these things are not given, for example n and efficiency, we can assume them and then go ahead. We'll see the overall relations. So Pelton wheel design, it starts with overall efficiency eta equal to P divided by gamma QH. This P is power at the shaft. This gamma QH is power because of gross head, that is overall efficiency. From this relation we have to find out Q, rate of flow. So Q is equal to P divided by gamma H efficiency. This is the first calculation. Second, we should know jet velocity V1, that is the z velocity V1. So we know that it is root 2 GH but multiplied by CV because there will be some losses at the nozzle point. That's why there is a multiplier which is known as a reduction factor, or it is most referred as coefficient of velocity. The value will be generally of the order of 0.9899. So that CV multiplied by root 2 GH gives the velocity of the jet once you know the head on the turbine. Then what should be the bucket speed? As we have studied earlier, for maximum efficiency, U should be equal to V1 by 2 or U equal to 0.5 times V1. But because of some practical difficulty, what is done is the relation or the ratio of velocity of vane divided by root 2 GH. This KU, which is known as speed ratio, is taken not exactly 0.5, slightly less, and this is in the range of 0.43 to 0.47. So theoretical value is 0.5, but we'll be taking it 0.43 to 0.47. Generally this value is provided. If not, then we'll have to assume. The angle of deflection is not made 180 degrees, but it will be taken as 165. So to say, our calculation for phi becomes something like 180 minus 165, that is 15 degrees. If it is 170 degree, then phi becomes 10 degrees. If 160 if it is, then the value of phi for our calculation becomes 20 degrees. So next, using U equal to pi d n by 60, this relation we can find out velocity of the vane. This velocity of vane is already found. Now using this relation we'll be finding out mean diameter or pitch diameter. This. Now here how it goes is we know that omega angular velocity is given by 2 pi n by 60. The u itself is d by 2 into omega. So if you club these two, you will be getting this. From here we have to find out diameter of the wheel. Then next, z ratio shall be of the order of 11 to 14. Generally it will be taken as 12. Now what is z ratio? It is nothing but diameter of the wheel, which is calculated here, divided by diameter of the jet. So that ratio is taken as around 12. Number of jets required will be equal to the total discharge required by the turbine, which we have calculated as Q in the earlier calculation, Q. Now that Q comes in the numerator. Then discharge of single jet. Now this D is calculated from this step number 5. This D, whatever jet discharge is there, that will be put here. So this ratio gives number of jets required. So this with this we'll be able to design the Pelton wheel. Let us see the examples in the next video. Thank you.